Hello everyone and welcome to our video presentation on quantum chemistry. Now, if you hear the word quantum, you would probably be like, yes, you're right. Quantum can also be about space and time and multiverses, but you can also apply quantum to other subjects as well, such as music, psychology, and even chemistry. But before we get into quantum chemistry itself, let's define what quantum is first. So quantum is derived from a Latin word quantus, meaning an amount. And quantum itself is the smallest discrete unit of phenomenon, and quantum science is also the total opposite of classical science. Well, if we talk about classical mechanics, we will usually refer to cars and people, and however, in quantum mechanics, we would usually refer to something like small, such as atoms and electrons. So, if classical mechanics refers to something that is big and heavy, well then quantum mechanics is gonna refer to something that is small and light. If changes in classical mechanics is considered continuous, meaning its property can change and it can move, well then quantum is gonna be something that is discrete. Their changes would be in a small scale and they will have a finite value where energy and atom can be. Overall, quantum usually deals with probability rather than having a definite answer. Now, before we learn how it behaves, let's learn about what atom is first. Well, let's talk structure again. Well, atoms, as we know, have three main subatomic particles: electrons, neutrons, and protons. Well, as you can see, protons and neutrons live in the middle. We call that the nucleus. Well, the tiny particle orbiting that nucleus is called electrons. And also, these subatomic particles have charges. The proton have positive charges, electron have negative charges, with an exception of neutron, which does not have any charges, and so we consider them neutral. Get it? Neutron, neutral. Haha. Now, the model I just showed to you is called the Bohr's model, which displays the atom having two main parts, the nucleus and the outer shell. The design for atoms has been evolving over the decades, starting with John Dalton and his first development of ideas of atomic structure deriving from an ancient Roman discoveries in 1803. But for simplicity, most classes use Bohr's model to display the interaction between atom based on its outer shell. However, the true form of electrons, arrangements, and its atom cannot be defined as an organized ring like in Bohr's model. And so, quantum model of atom was found by Erwin Schrödinger, also known as the cloud model, as the electron's position cannot be predicted, as we will elaborate later in the video.
Light allows us to see stuff. It kind of serves like a bridge between us and the universe. Seems like a huge thing, right? It originates from the sun and then it travels through and reaches us. Must be a huge thing. But actually, light stems from the smallest concept, which we now call the concept of quantum. So let's take a deeper look at what light actually is, and meanwhile, learn the basic idea of quantum mechanics.
Hi, it's Hyphen here. I think it's quite pretty dark in here. Wait, let me do one thing. Hi, it's Hyphen again, so you can see me more clearly, right? Okay, let's start with the first topic. So I would like to talk about the electromagnetic wave first, then the photoelectric effect. So our first topic, electromagnetic wave. Before we understand the term, I would like you guys to understand the term electromagnetic radiation first. So electromagnetic radiation is a form of energy that is produced by an oscillating electric and magnetic disturbance, or by the movement of electrically charged particles traveling through a vacuum or matter. Or in simple words, it is the emission and the transmission of the energy as in the form of electromagnetic waves. So from the example that I showed you before from the beginning of the video, you can see that when I close the light, you cannot see me clearly. When I open the light from my ring light and from the curtains here, you can see me more clearly. So I would like to tell you that the visible light consists of electromagnetic waves.
Wow!
So what is it? How does it make you guys see me? So the electromagnetic waves consist of the electric field component and the magnetic field component. So it will be combining and turn into this picture. Yay! So these two components combining into a perpendicular angle to each other. So it forms like a wave like in this picture that you see here. So both of the components have the same frequency and the same wavelength. And they don't need media to travel through anything. They can just travel through anywhere that they want. They can travel through air, through water, or through space. So there are many types of these guys, and they differ in wavelength and frequency. There are several of them, like gamma rays, X-ray, ultraviolet, visible light, infrared, microwave, and radio waves. So I would like to talk about this, starting from the gamma rays, which has about 10 to the power of negative 3 nanometer or 10 to the power of 20 hertz, which they have the highest energy and frequency. And as I said it from before, the radio waves we have the lowest in the both aspect, which they have the 10 to the power of 11 nanometer and 10 to the power of 6 hertz. So the gamma rays will be the highest energy and frequency, and the radio wave will be the lowest energy and frequency. However, as I say that the part, there is a visible light part. So I would like to elaborate this part. So from that, visible light is the light that you can see me right now. It consists of the colors that are in the rainbow, which are red, orange, yellow, blue, indigo, and violet. The violet has the highest frequency and the red one has the lowest frequency. So by this visible lights, they are making you see me right now. So this theory by Max Planck, which Lynn will talk more about him, can make us see things around us like here. However, there one theory that can be added to this theory, which is from Mr. Albert Einstein. So I would like to talk about the photoelectric effect. So this experiment is by Mr. Albert Einstein. So Einstein believed that light that are visible to us right now doesn't only consist of waves, but they also consist of in the form of particles called photons. So he conducted an experiment called the photoelectric effect or photoemission. So this is an experiment where electrons are ejected from the surface of a certain metals when they are exposed to the light. So take my hand as example. So this one would be the metal and this one would be the stream of light. So this stream of light contains photons. So when it hits the metal, the electrons in here absorb the energy and bounce off the metal, and they are ejected from the metal. That's why we got ejected electrons. However, the light needs to have the exact frequency. If they have the frequency that is less than minimum frequency, then no electrons are ejected regardless of the light amplitude. So it needs to meet the exact requirement of the minimum amount of energy, so it can set the electrons free from the metal. This whole concept of having the exact minimum amount of energy is called threshold frequency. In addition to this, the number of electrons ejected was proportional to the brightness of the light, which means that if we have the light that is really bright, we got more electrons that are ejected out. So to conclude everything, that's why Einstein concluded that the light that visible to us right now doesn't consist of only waves, but they are also in the form of particles called photons. So that's it for my part. Let's move to the next topic.
That most of people might have a question like this. What is the Bohr theory? And how about the Planck theory or the Planck constant? Why it's so complicated to understand? If you got like this problem, do not worry about it yet, because in this video I'm gonna explain the basic concept of each of them. As we know that the smallest particle in the world are atom, which consists of electron, proton, and neutron. In the 20th century, many researchers tried to push scientific boundaries by observing in the light-contracted areas. At that time, Niels Bohr, who was one of the scientists, came up with the idea that if an atom has a positive charge and negative charge of electrons, why they do not collide with the nucleus? Since the positive charge and negative charge will always attract together. In order to answer this question, he created a model that's called Model of Hydrogen Atom. This means that electron can have an imaginable energy, but only inhibit at specific energy levels. Each of them would have different value due to the number of proton and electron that would transition from one level to a lower level energy, when the photon of a very particular energy is either absorbed or emitted by the electron. So how can we know the change in energy of electron during the transitions? We use Hilbert constant to measure it. So as you can see the equation on the slide, the n with F is mean where the electron ends up, and the n with I mean where the electron begins. Beyond this, the member contains transitions that generate photons of visible light found in the hydrogen emission spectrum. As I said before that, every element will have its own emission spectrum due to the different nucleus. Therefore, Bohr theory will explain the compositions of an object in space by analyzing the light that we can see. So move on Planck theory. Max Planck, who is a scientific study about the ultraviolet spectroscopy under the topic of the nature of blackbody radiation. So what is a blackbody? Well, it is a hollow metallic shape coated inside a platinum black by having a small hole in it in order to act as a blackbody. A blackbody is really good at absorbing the radiation falling, and it's also good at emitting radiant energy, which both of them will depend on the temperature. Since energy associated with each quantum for particular radiation of frequency, so we have the equation to calculate it, which is E equal to hv. H is a Planck constant. It's about 6.626 times 10 to the negative of 34. So in the conclusion, we can say that the emissions of radiation is due to the variation of charged particles or electrons in the body. The emission is not continuous, but it decreases packets of energies called quanta. And the last one is the emitted radiation propagates in form of the wave. So here is a topic that we cover all of them.
We're going to be talking about electron shells. Hooray! But first, we're going to be starting at the atomic models. We're going to be starting at J.J. Thomson's plum pudding models. He stated that atoms are a charged ball with evenly scattered around negative particles. Ernest Rutherford and some student comes in to do a little experiment on it to prove him, and he proved him wrong. So Ernest Rutherford also comes up with his own model, which is called the nucleus model. He stated that an atom got its own nucleus in the middle consisting of positively charged and neutrally charged particles, with a cloud of negatively charged particles all around it. But there is a problem with this, which is what is stopping the negatively charged particle from merging with the middle? Niels Bohr came up with a solution, which is the electron shells, which he introduced into his own new type of models. Electron shells are a group of atomic orbitals. Think of a planet going around a star, or the Earth orbiting the Sun. Each orbital has its own specific amount of energy required for an electron to be orbiting in the ring. The higher the energy, the further the electron is from the nucleus, and the lower, the closer it is to the nucleus. The amount of energy gained or lost when moving through the shells can be summarized in the equation of delta E is equal to RH multiplied by 1 over n initial square, subtracted by 1 over n final square. RH is the constant of 2.18 multiplied by 10 to the power of negative 18. And it's a level initial being the starting level and then the final being the ending. Delta E is the amount of energy changes. If it's negative, the electron loses energy, but if it's positive, the electron gains energy. This also shows the direction of movement if the electron jumps up or down the shelves.
So Planck and Einstein viewed light very differently. Planck viewed light as an electromagnetic wave carrying quantum energy that can be absorbed or emitted from electrons, while Einstein described light as a stream of discrete quantum packet of energies with a particle-like behavior. So let's make things clear here about what light actually is. Light a wave, like ripples on the pond, or is it particles like electrons? Or both? The answer is neither. Light from the two experiments possesses both the property of particle and both the property of wave, and that's why we call light having the property of particle-wave duality, meaning that even though it shares some characteristics with waves and some with particles, it is considered neither, but rather its own thing. Guys, we're talking about quantum objects here, right? We know that in tiny objects, normal rules don't apply, and that's the whole reason why we come up with quantum field in the first place. Quantum objects are their own things. Don't try to put them into particles, don't try to put them into waves, put them into quantum. They are quantum objects. It's like you have a mole. Is a mole a donkey? Is a mole a horse? No, it's a mole. It's not both, it's a mole. In quantum field, we keep looking into the smaller parts of the object. And so we want to know what light actually is, we need to look into the smallest part of light. And now we know that the smallest part of light is called a photon. You want to know what light is? Let's talk about photon. So photon, by definition, is a quantum packet of energy in light. But that's not all, because we can literally say anything is a packet of energy. So I can say it right here that I have a packet of energy inside my bag. Is it a light? No, it's a marshmallow, alright? It's a food. Food is also an energy. So I made my point, right? In order to correctly understand what photon really is, we need to look into the details of the energy itself. It's the details that make photon special. Photon first has a charge of 0 and a rest mass of also 0. These unique properties allow photons to do many unimaginable things, like traveling through time and space with a speed of almost 300 million meters per second, as known as the light speed. Light's pretty cool, huh?
Okay, so on to the next section, the thermoelectric effects. The thermoelectric effects are the effects that entail a conversion between temperature and voltage when a thermocouple is involved in a circuit. In the passive mode, we find that energy is actually generated by a thermal differential across the two sides of the dissimilar metals, while the energy, if we put it in, will cause a temperature differential across the two sides. The thermoelectric effect relies on two main principles, the first and the second, but both of them rely on one important concept. That concept is called the fermionic energy concept. It's the Fermi energy concept in other terms. Essentially, it's a concept in quantum mechanics referring to the HOMO-LUMO gap, or the difference in the energy between the highest and lowest occupied single particle states in a quantum system of non-interacting fermions at absolute zero temperature. This is only a theoretical value because we have no way to measure it, but anyway, moving on to the effects. The first is called the thermal power or Seebeck effect. The thermal power or Seebeck effect states that when two dissimilar metals have a junction together and both of them are conductive, the thermal gradient maintained will cause an electrical differential due to the electrons jumping from one material to the other. Anyway, nextly is the Peltier effect, or Peltier effect, depending on if you're English or British. That effect is the effect that energy, when passing through a junction between two dissimilar conductive metals, the energy will create a thermal differential, which is the second part of the Peltier, or what we see observed happening. Anyway, all this is shown in the diagram, which is going to be here, right? And let's talk about applications next, because thermoelectric coolers have a lot of applications. They have applications in space technology where temperature needs to be accurately regulated to the precise half a degree, because they can both heat and cool depending on the direction of the voltage flowing through them. In addition, they have very predictable curves, meaning that they can both very linearly predict the temperature of an object and give feedback to actually heat or cool it to perfect temperatures. Other than that, thermoelectric coolers are also used in power generation in some space technologies, such as satellites, which have nuclear reactors with a quotation mark, because they are singular objects which are capable of producing heat. When that heat is applied across the gradient to space, we find that energy is generated, which is enough for the satellite to live. Anyway, the next effect is called the superconductor effect. The superconductor effect is the effect, or it's a set of physical characteristics that we find in a specific type of materials exhibiting zero resistance at its critical temperature. And unlike ordinary metallic conductors whose resistance decreases gradually, again, the resistance is non-existent at their critical temperatures or below them. This is because negatively charged electrons, which normally repel each other, pair into each other at the critical temperature. These paired electrons are then held together by atomic level vibrations, which are known as phonons, and collectively, the pairs can move together through the material without resistance because of it. Anyway, what you're seeing here is a levitating magnet on a superconductor, which is cooled to below its critical temperature. You can see that the magnet is actually floating what appears to be in the air, because the eddy currents are going around the material and not actually through it. Thus, it is sort of levitating by pushing. Let's explain the superconductor effect while you watch that guy try to poke it around. When the material is cooled down to below its critical temperature, we find that the superconductor will expel all magnetic flux, and this is called the Meissner effect. In essence, when a permanent magnet, such as a cube, which is shown here, is brought close to a material, its magnetic field lines will penetrate the material. However, when that material is a perfect superconductor at absolute critical temperature, the superconductor now contains a mirror image of the permanent magnet due to the induced currents and resulting magnetic field. You will find that the magnetic fields get expelled, which exactly cancel out the magnetic field of the permanent magnet. This repels the magnet, and the balance of the repulsive and the attractive gravitational force pulling it down will cause the magnet to levitate above the superconductor. Some uses of superconductivity are magnetic resonance imaging, nuclear magnetic resonance, particle accelerators, magnetic fusion devices, and electric power transmission generators.
Just want to leave an end note here and say that tiny things bring tons of troubles, but we can't just ignore the quantum world, because we need to thank quantum for many things that we use in our daily lives, such as our phones and our computers and even our toasters. Yeah, the thing we use to bake our bread in, yeah, the toasters are a perfect illustration for quantum mechanics, the glowing of the rod. So next time you bake your bread, thank quantum mechanics. That's all. Nope, that's not all, because there's never all for quantum. To quote Richard P. Feynman, if you think you understand quantum mechanics, you don't understand quantum mechanics. And that kind of stinks, because that implies that this whole video doesn't make sense because we don't actually understand quantum mechanics. But I do really hope that you understand a little, and we do our best as grade 11 students explaining about quantum world. Thank you.